Okay, so the second part is I want to talk about another thing where compactness comes up. It again comes to the rescue, sort of. That if you think of examples, things fail if the sets are not closed, things failed if they're not bounded. And one of these cases that's very classical is distance between sets. And what is the distance between sets? This corresponds to the usual notion. So informally, this is sort of like the distance from Finland, where I'm now, to the USA. I mean, Finland and USA, they're not points. So you cannot make sense of distance between points. They're collections of places. So what does it mean to take the distance between them? These beautiful two maps. Well, it means that you take the closest points among them. And I would guess that it's probably somewhere in Maine and somewhere in Lapland, Finland, that you have the closest points. So it's just the shortest distance that you can go from any point in the space, from some point in the space to another point in the space. Of course, there are points that are much further away. So Los Angeles is much further than Maine from Finland because it's on the other side of the country. So this, so distance between sets is a mathematical notion that captures this idea. So how is it defined? It is distance between A and B are subsets of some metric space, just so we can talk about the distance. But in this class, I'll just think of R2, the plane, and R. So you don't have to think more generally for this class, and it's more, all the examples will be there. And so it is, you take all the points in A and all the points in B, you minimize the distance between A and B, letting those points vary in those spaces. Okay, let's do some specific examples to show that when things work out and how do they look like. So if we have A is the closed interval, sorry, my internet disconnected for a little bit. So it is in the plane, it is the closed interval from -1 to 0 times 0. And then I have B is a square, here I need also times 0. B is a square that starts at 1, goes up to 2, and then lies symmetrically on the axis. It's really a rectangle, roughly like this. So from -1 to 1 on the y-axis, and then on the x-axis, it goes from 1 to 2. So this is B, this is A. Now, what is the distance between them? Well, you take the closest pair of points, and after some examining in simple geometry, you could conclude that the closest pair of points in this case is 0, the origin, 0, 0, and 0, 1. So the distance between them, in this case, it's attained by a specific pair of points. It's 1. Now, if you took away these endpoints, so in this other second example, and this is kind of the issue that I want to talk about more, is if you took away these endpoints, so you replaced A by this open interval times 0, you took away the boundary from B, so you made it the open interval 1, 2 times -1 to 1. And what you get is, well, you have the distance between the interval from -1 to 0 times 0, so this is on the x-axis. And then you have this rectangle from before. But now you're not including the endpoints, so those are holes in the set. Well, the distance is still 1, but it's not attained. By some A in A or B in B. because the points that would attain it, they are outside of the set. And by what I mean by points that would attain is if you took a sequence of points that where the infimum is attained, which get closer and closer to each other, they would leave A, they would leave B, respectively. This is often always the problem with optimization, is that the relevant, if the sets are not closed, then somehow the attainment might happen at the boundary of the sets. But there are much worse examples. So one of the worst example is, this is again in the plane. And let's draw the set A in red. So A is the graph of x1 over x. So it is a closed set. It is not an open set, as you could verify. And B, sketched in blue, is just the y-axis. And B is also closed. And it's worth mentioning that A intersected B is empty. So these don't have any common points. However, distance between these two sets is 0. And where the pathology is happening is as you go off to infinity. So here, if you take a sequence of points that sort of go up this funnel, then pair distance between them goes to 0. So you have the infimum of all the distances is 0. Of course, it's not attained because you don't have any common points. So this kind of issues can happen. Distance can be 0 for disjoint sets. It cannot be attained if you're not open. And another thing that can happen is, and it's really kind of an unfortunate thing about the terminology, is that the triangle inequality can fail. Namely, if you have A, subsets of the real line just, then the interval 1 to 2 is B, and then C is 0.3, then, well, what is the distance between A and B? It's the smallest distance between the single point of A and any point of B. So it's just 1. Distance between B and C is also 1. But what is the distance between A and C? A is the singleton 0, and C is the singleton 3. It's 3. So the question, is the triangle inequality true? Well, no. So no triangle inequality. So these should ring, I mean, at least you should be careful when you are using this term distance of sets, because disjoint sets can have distance 0, and that there is no triangle inequality. In particular, this is not a metric. Distance between sets, this way defined, is not a metric. There are some other distances that would be so-called Hausdorff distances, if you want to Google, that fix this problem, but they're much more complicated. And they are not what corresponds to our common notion of distance between sets. So distance between sets is not a distance function in the sense that we introduced in our first lecture. It does not define a metric space. But it is a useful notion for other reasons. Okay, so again, in these examples, except, well, the first example was kind of nice, but every other example, something went a little wrong. So what can you salvage? So what to kind of chart what is good in this case, you can still prove that if you have compact sets K1 and K2 that are not empty, disjoint, and compact, then there exists an A and B in the first set K1. There exists a B in the second set, such that the distance between the pair of points is equal to the distance between the sets. So there exists a closest pair of points. And the main issue is exactly these two examples here. Here, the distance is 1, but it's not attained. Sorry, in this picture, the distance is 1, but the points lie outside the space. That's the closedness. If you drop the closedness, and if you drop the boundedness of the compactness means closed and bounded in, then you get these situations where the sets can approach each other, but very far off into the set. So in this case, the distance is 0, even though no pair of points realizes that 0. So the question is, again, whether infimum is attained and compactness comes to save you. But to make sense of this and to connect with everything that we discussed, we don't want to think about separately about optimization problems that involve two sets, or choosing a point in one and choosing a point in another. So the language to discuss that is to introduce the idea of a product space, which is really the space of all pairs. And as a set, it is just the collection of pairs, x, y, such that x is in the first set and y is in the second set. This is generally the product of two sets, and it's the collection of pairs. So the idea is that we create a space that contains the possible combinations of K1 and K2, or the possible pairs. And this way we can actually infimize over this space instead of infimizing over individually these two spaces. Now, if we want to use our language of metric spaces, if we want to use open sets, etc., we have to introduce a metric on this space. So we have to have a way of measuring if X is a metric space, if Y is a metric space, in the product, so the space of pairs, we have to have a way of measuring distances between these. So specifically, if we have 2 points, x1 and y1, and x2 and y2, well, we know what is the distances in the x components. We know what is the distance between the y components. What do we call the distance in this product space? Now, it doesn't have to be in the plane, but this is a scheme indicating what generally this looks like. And the most usual thing, certainly what you can always assume in this class, is square root of the distance of the x components squared plus the distance of the y components squared. So this is kind of like a generalized Pythagorean identity, but we just define this as the distance. Now, one can verify that this is actually satisfies the triangle inequality. That's a fairly involved proof. You can say see Pugh's book if you want for that. Now, it's not the only metric. It's worth mentioning that there are other distances, maybe 1, 2 of them that are quite commonly used, and you can use these as well if you want, depending on your application. The easiest one is you just sum up the distances. And actually, this one is probably the easiest one to verify the triangle inequality with. This is also related to the so-called taxicab distance. But then other distances is you look at the maximum of the two distances. Or generally, if p is between 0, 1 and infinity, then you can look at the distance, define the distance as the pth in terms of using the pth's powers instead of the square. So pth power of the distance in the x components, pth power of the distance in the y components, and then everything to the 1 over p. Now, good news, it doesn't matter what you use. They're all the same. So to formulate one theorem to this extent, if you have a sequence that converges in the product with respect to one of the metrics, then it converges with respect to every other metric. This is exactly analogous to what we proved in Rn. In fact, it's a generalization of the fact, and you could prove it exactly the same way. Now, convergence, it doesn't matter which metric you use to define convergence. It doesn't matter which metric you use to define open sets. So this is like in your homework 1. If you have comparable metrics, they define the same open sets. This is essentially the proof. Then if you have an open set in one metric, then it's open simultaneously in any other metric. So every notion that we've defined so far, open, closed, compact, convergent sequences, they're identical, independent of the metric. So one could say that they define the same topology, or for the perspective of this class, they're exactly the same. It doesn't matter what you use. So you can use whichever is easiest if you want. So if it's open in one metric, then it's open in the others. Okay. So it doesn't, but usually I use this D2 metric because it's the most conventional one, even though it's a little bit messy. This way we also are always, if one of the factors is R, then we are in agreement. So you can prove things. Our time is pretty much up. There's just a scheme of here that you can quite directly fill. It's a good exercise. If you have a sequence of points and some possible limit, then converging in the product space is exactly the same as component-wise convergence. So this is, we again saw this in Rn. So this proof is exactly the same. You fix an epsilon, you suppose that you converge, and then the crucial estimate that you use is that distance in the x component is at most square, if you make it larger by adding this other square and taking a square root. But this is the distance between here. And now you can make this distance sufficiently large by an appropriate choice. So by what choice? Once you write that out, then you essentially have the proof. Okay, and we don't have this time to discuss this, but if you have compact spaces, then their product is compact. There's a sketch of proof. Here, you can try to fill it in. It's exactly like we did in Rn. It's exactly like in Pugh's book discusses this very nicely in this section of product spaces. It's a fairly brief discussion, but just to conclude our discussion and to wrap everything up, if we go back to our original setting, our problem was proving this theorem, that if you have compact sets, then the distance is minimized. Well, how is it done when we use this language? Well, our space that we're optimizing over is the space of pairs. Our function that we're minimizing is the distance function that is now a function of the pairs. Well, we want to apply the usual EBT. You prove that F is continuous. We just stated that the product is compact. We did not prove it. And well, since F is continuous and the product is compact, by EBT, we know that it contains a minimum. And this minimization is exactly what we wanted to say. So it contains a minimum. And so there exists a pair of points, x min, y min, such that the distance between x min and y min is exactly, well, this is the function value at that point, which is the infimum. So it's just shuffling around words. But using this language, this proof becomes a very short thing and you don't have to redo it again. So this is the end of the lecture. I'm happy to take questions, especially since we went over some things very quickly. But if you want to stick around, feel free to ask a few questions, either in the chat or by unmuting yourself.
Professor,
Hmm.
for the like first proof you showed in class, the one that you like found that showed the error in because you can't assume that xn converges.
Hmm.
Why
Yeah.
is it again that you can't like could you just go over again why that was wrong? Is it because it's not um like why are you not able to say that xn converges? Is it just because you're not saying that like is it due to
Uh,
compactness?
so, well, so we know that yn converges to some y,
Mhm.
and then each of the yn lies in the image. So we do get some xn such that f of xn is equal to yn. But xn is now just some sequence in f, and it need not, we don't know anything about it anymore.
So it's not that it doesn't it's not that it just it doesn't need to converge.
Exactly. Yeah. It may
Okay, okay,
converge,
gotcha.
but we don't know that it, yeah.
Okay,
There's
we
no
just don't know.
assumption that would guarantee that converges, and because we don't know, uh, it could fail. And that's also, I mean, if you say, think of this example here,
Mhm.
that's kind of the counter example. What happens here is that, okay, well, the image set is not closed, so you can take a sequence of points here that converges to 0.
Mhm.
Okay, it does converge in the image side, but what happens for the pre-images? Well, they go off to infinity. So these are the
Gotcha.
xn's, those are the yn's. So even though the image points converge, there's, in general, you can create examples where the domain side does not converge. Now,
Okay.
if the domain is compact, then that restricts it so that you can still get enough convergence that it all works out. But so.
Okay, thank you.